Oh, you are using two different camera for different angles?
Yeah.
Oh.
Yeah. Because it's an option.
I'll quickly go and 1:30. You have to leave here 1:30 or 3?
Yeah.
Okay. Yeah. Okay, then let's get started here. So, everyone remember we talked about the intensity from scattered light of atoms, right? So this is the important thing to start with. That intensity is proportional to the square of your something called the Fourier transform of the charge density, right? That's the important thing. So you should be write this one as rho g. So we know g is a function of HKL, right? So this is the intensity of the scattered light of these electrons, right? If you have something with electrons, you have this wavefront coming. The scattered intensity is the square of this Fourier transform. You know how to write the Fourier transform, right? How to write rho g? Everybody should know how to write the Fourier transform. Basically, this is your charge density minus I. Actually, we showed this is delta k, right? Delta k dot r times dqr, right? Is the Fourier transform of this rho r. So then, if you remember from the first few classes, since these are this periodic atoms, we can always write rho r, because rho r is basically rho r plus t, right? That's the translational symmetry. So that's why we could write this one as, if you remember, rho, we'll say some, ag I wrote. Here I write like rho g times e I g dot r, right? For different g vectors. This you can only write if you have a periodic function. So if you compare these two, because here rho r, you can write this way. So here you have delta k. So if you compare the two, you can say delta k is nothing but g, right? So this is same as the Bragg's law, like 2d sine theta equals and this one are the same thing. So right now, this is what we discussed in the last class. So what you need to understand is your scattered light intensity is the square of the Fourier transform of the charge density square. That's all, right? So this is the Fourier transform of see, it's the Fourier transform. This is the important thing, right? Your light is getting scattered by that electron density. Okay, so now let's go ahead and, so from here onward, I will use that your intensity, this rho g squared. Rho g I only write as this rho r minus I, not delta k, g dot r, right? Because k and delta k and g are the same. Okay, so that's all we need to get started from here. So now, rho k is this. Forget about this normalization factor. Then also we talked about, if you consider the entire solid, you cannot consider each atom, right? So what we do, we only consider the one unit cell. So that means you can write this the rho g, this integral you can only do in your one unit cell. You don't have to integrate all of them. You cannot do that, right? You only do for one cell. That's it. So let's start from here. Very straightforward. So so now to make this little bit simpler, so how do you do this cell? Considering all the cell, that means if I take my cell here, this is my unit cell C, then I have different atoms, right? This is basis, right? So we'll call one atom here, one atom here, one atom here, like that. That's the unit cell, right? So I'll write this position of that atom as R alpha. That means R1, R2, R3. This is right. R alpha is the position of the basis atom, right? So now, if you consider, because this is my R, right? So R is basically, this is my origin. So this R you can write as actually R alpha, but this is not a point charge, please remember. This is a electron distribution, right? If you take a atom, suppose your nucleus is here, right, positive, then your charge can be cloud, right? Suppose if you have like p orbitals or something, it can be something like these are charge is not a point, right? So that means rho r, basically we are talking about something at this point r. So for that reason I will write this r as r alpha. R alpha is from here to that the electron has some charge, right? So this part I write as r prime, right? If it's a point charge, r alpha, the r prime is 0, right? There's nothing, but I can write r as r alpha plus r prime. R prime is what? From the atomic position to that some point here in this electron distribution. Is this clear? So now this one I can write as my rho g as in the cell I have several atoms, right? That means I have to sum over all the atoms. So that means I have to say over alpha. So then I can write rho r. Now only depend on rho r prime, right? With r prime is r, this is a constant, okay? So then you have E minus I G dot R means now R alpha plus R prime, right? So then dq R prime, but you have to integrate all over for all the basis atoms in the unit cell. Is that clear? So you understand this one, right? Now it's become only a function of R prime. This is only because this is constant, right? So that's it. So now if you write this one, I promise you this only integral I'm doing. So now you can write this rho g as what? Rho g is, I can write this one. This one I can write as Ig dot R times Ig dot R prime, right? So that means I can write this one, some alpha, I can write as E minus I G dot R alpha, right? So then I have the integral part, I have rho R prime, then I have E minus I dot R prime coming from this part, right? This is the first part. Then I have dq R. So this is basically what is in that electron distribution. So this is basically summing of all the atoms in the basis. So typically we define this factor as F R. So let's see. Yeah, let's. I can exactly. You can understand from here, right? What I wrote here is exactly what you have here. So we write this one just F alpha. Yeah. So then your answer will be basically, this is simply F alpha. So this is the only thing you need to understand in this rest of the class. So you can write this rho g as alpha E minus I G dot R alpha times this F alpha for given. So F alpha is what? That tells you how the charges are distributed. It's not a point charge, that's the only thing to understand. So this we call the atomic form factor. Atomic form. So then what is the intensity of the scattered light? Square of this one, right? Just remember, I is simply rho G square proportion. So actually we call this one as, because this has a function of this F alpha, we call this function as F, that since it depends on G, we call this HKL. This whole thing is called the structure factor. So what is this? This basically number of atoms in the basis, right? So this tells you each atom. Suppose if you have, say, carbon atoms, like diamond, right? So you have 8 carbon atoms, they all have the same F. But if I take silicon carbide, still diamond structure. What do you call that structure? Zinc plane structure, right? So for that one you have alphas different. That means silicon I have one value, carbon I have different value. But if you have the same thing, your alpha can be same for every atom. Okay, so then the intensity would be basically FHKL the square. So we call this one structure factor. This one is called the atomic form factor, scattering factor. So you understand this. Alpha means, in this case, how many alphas are there? Only 3. Alpha 1, alpha 2, and alpha 3. You have to just sum over these 3. As simple as that. You can understand this one this way. Suppose I have these atoms, say, so I have alpha 1, alpha 2, alpha 3. Let's see. So now I have this light coming with wave vector, say K0. Now each of them will scatter this. Suppose this is here. Scatter like this, right? So because this one has some density here, right? So suppose then each one will give you some kind of phase difference. So that means this one can give you some EI, say some phase difference pi 1, this one can give you pi 2, EI pi 3, like that, right? So that means ideally you can represent that structure factor as something adding as vectors, right? Because that's a complex numbers, right? How do you add complex numbers? Either you can add as phasors or you can use simple complex number addition, right? So typically you can represent, what is this F1 times this one means? So actually I can write this one F1 times this one, F2 times F3 times. If they were point, you don't have F's, right? If they are extended charge distributions, you have F1, F2, F. So that's basically what this one. This is the scattering coming from the first atom, right? So second atom. So then if you want to get the total F, that means you have to sum all over from all these scattered, right? You understand what F means, right? Okay, so let's just remember this equation. That's all you need to understand from here. So next what we are going to do is, using this one, we are going to calculate the structure factor for all the crystal structures. So to do that one, we'll find some general equation. I can write G. Anybody remember how you write G? H times B1, K times B2, L times B3, right? So we know how to write B1, B2, B3 in A1, A2, A3, right? Then what is R alpha? It's a position vector, right? So let's see what they use. I think they use UVW or something. Yeah, they use UVW. Yeah, R alpha you can write as say U alpha A1, right? That is in the real space. U beta, for different R you can write as U, probably write it, U alpha, B alpha times A2 plus say W alpha. It's the positions, right, of the basis vector. So then if you take this one, what do you get? Then I can write, so this is the position, right? Position of each basis term. Then I can write my F as HKL as alpha E minus I. When you take the dot product, what do you get? A1 dot B1 is what? 2 pi, right? Any of these will be 0, right? Remember, this Aij is delta Ij times 2 pi, right? Only when they are equal, it is 2 pi. That means if I multiply these two, I get H times, say, U alpha times 2 pi comes out, right? That 2 pi, then I can write 2 pi times, what do you get? H times U alpha times here, so only this one comes, right? K times B alpha plus L times W alpha. That's it. If you know this relationship, you can calculate very simple. So that's what here. So alpha they write like I, don't worry. Yeah, you understand what. Is that clear for everyone? Okay. So now, yeah, here I just write. So this is the equation I'm going to use throughout. So don't worry about the negative sign. So I just put the positive, so that doesn't make any difference. Here only I wrote instead of alpha, here I have I. The same thing, right? Please remember, that's the only equation you need to know. But you need to know little bit of some identities. Yeah, these things, everybody should remember this one. Everybody remember this one? Any odd number of pi times I is always negative one, right? Any even number of i's 2 pi, 4 pi, 6, that's always plus 1. So then we know how to write this one. E pi is negative 1 times n if you have. Get here, this is also true. So you should remember these identities. So also another identity I haven't written here. Please remember these identities also. We know E Ix is cosine x plus I sin x, right? So that means if I have I pi is what?
Cos pi.
So cos pi is minus 1, right? So that means this is always minus y. If I have I pi by 2, cos 90 is 0, then sin 90 is 1. This is I, right? Yeah. This relationship, please remember these things. This is I. So because those things should come handy when you do the quick calculations. So let's calculate some simple things. Now let's think about simple cubic structure. So that means you have only one atom per unit cell, right? But we know the location of all the atoms. So then how do we calculate the structure factor? So your atom, because you have only one atom, right? So that means you can pick whatever the position you want. I'll take that one atom at 0, 0, 0. Remember, this is a simple cubic, means you have only, this is a primitive cell, right? One atom. So I pick that my position of that one atom as 0, 0, 0. That means your U alpha is 0, V alpha is 0, W alpha is 0. Right? That's the position. So then just when you add, you only have one term. Alpha is only 1, right? So then when you add, what do you get? FHKL is, oh, here I didn't write, oh, sorry, this is alpha should be here, right? So what you get here is, so only one term, then I have F times E minus, I'll just use a plus, doesn't matter which one. So then what do you get here? 0, 0, 0. That means E, so E I to the power 0 means 1. So this is basically F. That means for simple cubic system, you always, your intensity is finite. You can never get any 0 intensities. For simple cubic, you will have all the possible reflections. Because you get finite F, right? If this is 0, that means you don't have any scattering. Yeah.
So that's at the origin?
Yeah, because I can pick any point.
Okay.
Yeah, I just pick 0 to, because there's only one atom, right?
Right.
So when you do next one, you get. But now let's make it a little bit complicated. Still simple cubic, but 2 atom basis. Anybody remember what kind of structure we had for that?
The 2 atoms.
Remember cesium chloride? So it looked like BCC, right? But it's a simple cubic with 2 atom basis. So let's do that problem quickly. Again, this one. So since I have 2 atoms, I take one at 0, 0, 0. Next atom, say any arbitrary place. So then, how do you calculate? Now you should have how many terms there? Alpha? 2 terms, right? So first one, so this 0, 0, 0. If you put that one, you get exactly this F value, right? I say that is FA, because I just put 0, 0, 0 here, right? Next term is what? I say that is alpha is 2 now, F2. Then what do you get here? E minus plus I2 pi. Then what do I get? H times, they say it's XYZ, right? Then I have HX plus KY, that is the position, right? For any general position here, plus L times C, right? So that is your structure factor. So, but can you tell me what happens if this HKY, suppose my these are suppose in a position like some half 0, 0 kind of. Suppose X is, if it is this position, 0, half, 0, then what happens? Then X is 0, right? So this 0, C also 0. What is this one? Half. That means that half and this 2 cancel. What do you get? Pi I. That means that becomes -1. So that means you have FA minus FB. Now you can see, if you have same atom, your intensity will be 0. But if the atoms are different, they are non-zero, right? So actually that's very important things. Let me show you. So look at this one. This one. So this is actually simple cubic with 2 atom basis, right? What is the position? One I can take as 0, 0, 0. Other one is what? Half, half, half. If you put half, 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 again that becomes 3 over 2. Then 2 and 2 cancel, you get 3 times pi. That means negative 1. So that means it should be 0, but here these two atoms are different. Then they are not 0. That's why you can see if I have same atom structure, so you will not get these values, because if you add these two, they all are odd, right? 1, 0, 0 means 1 plus 0, that's 1. That means that you get pi, right? Here 1 plus 1 means 3. So again 3 over 2, they cancel. So here 2 plus 1 again 3. That means you get this number, right? So if they are same atom, this will be 0. You don't get that. But if they are different, you will see this structure. That's why if you have this kind of structure, you will see these reflections. But if they are the same atom, you will not, right? Because they are 0. We'll talk about that one later. Okay, that is for simple cubic with 2 atom bases. That clear? So in this case, actually, the one I showed you, what are x, y, z? Half, 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 right? One was 0, other one was half, half, half. If you take that one, you can see half, half, half. Then you get, when you cancel with this one, you get odd number, right? That's why you get negative number here. So now let's look at the body-centered cubic. Now, in this, still we can consider this one as simple cubic with still 2 atom bases, right? So now again, if you plug in those things, what do you get? You get one coming from the 0, 0, other one coming from half, you can see cancel, right? You get H plus K plus L. Now, if you look at this one, what do you get? Just imagine H plus K plus L is a even number. Then this becomes plus. That means they add up to get, this part becomes 1, right? But if the sum is odd, what happens? Then this becomes negative. So that means that becomes negative 1, then 1, here 1 plus 1 becomes 2, here 1 minus 1 becomes 0. That means that's very important. If you have a simple cubic, if it's a one atom basis, any reflection is allowed, right? If it's a simple cubic with 2 atom basis, with your atoms are different, so still that some ones is allowed, right? But in the case of BCC, you only get reflections when these 3 indices, the sum is even. If they are odd, you don't get any reflection. Please remember, I will give a list. BCC, H plus K plus L should be even. Then only you get the enhanced scattering. So these are fine, right? What is this one? 1 plus 1 is 2. 2, 0, 0 is 2. 2, 4, right? Here 2 plus 4 plus 2 is 6, even. 4 plus 0 is all. These are all evens, that's allowed. You cannot have 1, 1, 1. Then your sum will be odd. Then you get, is it clear for everybody? So now let's look at FCC structure. Now if you look at this one, you actually, you have one at the 0. Then what are, we have the other 3? You have 6 faces, right? So 3 faces, you can have that half of the center face, right? Like this one, and the one here. You don't have to consider both faces, right? That's the same. That means you have one at 0, 0, 0. Other one maybe half 0, half, half 0. Other one is half 0, half. Other one is 0, half, half, right? These are only 4, so you can see. Yes. So now if you plug in these things, you can see, if I put the first one, you get 1, right? So other one you get, this all, because of half, you get the 2 and 2 cancel. But here I have only the K and L, H is 0, right? So K plus L. Here I have only H and L, no K here, right? So here, you get the idea, right? So now if you look at this one, how do we get this one? You can see if suppose all the indices are even or all of them are odd. If they all are even, that means this one also even. Even becomes even, right? So that means this becomes 2, that means plus 1. This one plus 1, this one plus 1, you get 4. You get 4 of them. If all odd, that's also fine. 2 odd numbers, when you add, what do you get? Even number, right? So then they all become positive. So, but if you have mixed indices, maybe 2 of them even, 1 odd, 1 is even, 2 odd. In that case, you will see 2 of them, they become 1 minus 1, other one plus minus, right? You have to try that one. So then you get, they cancel each other, you get 0. So if you have FCC, you get reflections when either all the indices are even or all the indices odd. In the BCC case, the sum should be even. Please note the difference, right? So you can see here, look at this one. The 0 is considered as even. So they all are even. Here they all are odd. Here they all are even. They all are odd. All are even. Please remember, either all should be even or all odd. You cannot have any mixed indices. So now if you consider diamond. So diamond, what is the situation? Like I said, diamond is more like 2 FCC lattices you just interlace, right? You can push it by in the diagonal direction by quarter distance, right? That means you have 8 atoms. So here I just put it in a different way, like put in like 2 different lattices, one at 0, another one this shifted by quarter. Or you can write 8 atoms. So this is FCC, right? So you can have just like before half, 0, half, 0. So like that, then you can have everything is shifted by quarter. So that means you can have maybe 0, 3/4, then you can have 3/4, 0, 3/4, or you can have 3/4, 0. Like that you get the same answer. So if you do that one, you get this equation. So if you can write this way. Now you have to understand that I is coming, right? Whenever you have I pi by 2, that is where I is here. You can calculate this one. This is what you get. If you are, because diamond also FCC, right? So that means it should follow that FCC thing, but there are some additional features you have to satisfy. Here, by looking at this one, you can say, just like before, your all odd or even, that situation is true, but important thing is, in the diamond case, the sum of these 3 should be multiple of 4. That means you cannot have like 2. 2 is not a multiple of 4, right? So you can have like H plus K plus L should be 4 or 8 or 12, like that. So other than that, that's more like FCC structure. As for FCC, allowed reflections have HKL either all even or all odd, but additional requirement is the sum of H plus K plus L should be the multiple of 4. That's the important thing. I'll put one nice table, it will summarize everything. So if you take a hexagonal close by HCP structure, that's what the homework was about, right? Again, you can write this one as a 2-atom basis. So you can have one at 0, other one is actually a point here, half of C, then 1/3 in one direction and 2/3 in the other direction. So that's basically 0, 0. Then you have half in C, other one 1/3 and 2/3. If you put this one, you get these requirements. But we are not going to do this calculation. This is a bit hard. We are only going to concentrate on cubic structures. See the simple cubic, FCC, BCC, those kinds of. But it's good to know what this should be. Actually, in this one, you will find so anything you have this L odd, you cannot have any reflections. So then I will put together some other requirements. But don't worry too much about this one. But you know how to calculate that one, right? Okay, so next thing is, if you remember I talked about FCC, you can have either all odd, all even, right? So, but if you consider, so this is the one I talked about, the BCC, actually the simple cubic with different atom bases, so you can have these additional ones. Even for the FCC structure, if you consider potassium chloride and potassium bromide, yes, we know sodium chloride, right? Because the rock salt structure, that is also FCC structure. But if you, similar structure is potassium chloride, but I want to consider potassium chloride and potassium bromide. So if you consider potassium chloride, actually potassium and chlorine ions, the structure factors are very similar. Fa and Fb are same, but if you consider the potassium bromide, this Fk and Fbr, these are not equal. You can see now if we have something like this, if they are equal, this becomes 0, right? If they are not equal, they are non-zero. You can see actually if you look at this one, so if you take potassium chloride, non-zero if all indices even. We know for FCC, you need to have either all even or all odd, right? So here for all the even indices, you have these peaks. So, but for the potassium bromide, yeah, so here you can only get that whatever that requirement, right? But in the case of potassium bromide, since Fa and Fb are not equal, things that you don't see here, you will observe here. You can see these peaks, like all these things are here, but there are some additional peaks like 311 and some peaks I have to see here, like 111, right? So then 3, yeah, I cannot see here. I mean, I can see it clearly here. Yeah, you have 331, then I have 311 and 111, right? 331, then I have 311, then I have 111. So these are all odd numbers, right? So they all are odd numbers, but you can have those reflections because the form factors are different. Okay, next I want to talk about structure, how to calculate the structure factor for sodium chloride. We know how to calculate for FCC, right? But sodium chloride is a little bit more complicated because if you consider sodium chloride, remember, this is the structure, this is the unit cell. How many atoms are there for this unit cell? So, no, but in this case, you have actually 8 of them, right? So, how do you get that? So, these are chlorine atom, these are sodium atoms, right? If you take chlorine atoms, you can have, actually no, we have 12 atoms per unit cell, because chlorine you can have 6, because sodium atom, please look at this one. So they are at each center of each this line, right? So that means you have 12 the lines there. So that means you have 12 means you can get, you don't have to consider both sides, right? You have 6 atoms for sodium, for our chlorine, no, I'm making a mistake here. No, that's fine, yeah. Chlorine, then, sorry. How do I get that one? You can see, if you consider these edges, you have one coming from the corner ones, right? One coming from corner, then you have one coming from this face centered one, right? So that means you have half of 6 faces, right? So then you have, there are 3, 4, then you should have one at the center. So 4, 5, how do I get it? Actually you should have 6. Yeah, actually I have that one written here. You can see. You have to look at this one carefully. Actually in this one, yeah, here. So these are, yeah, here. You have actually 8 of them, not, sorry, yeah. 6, 7, 8, yeah, that's fine, yeah. You have 8 here, then this one also you have 8. How do you get 8 here? Sodium, you can count this one, yeah. So these are the position of that sodium, so one at the center, then at every, these are the at every face centered position, right? So then chlorine atoms are all in that middle of that edges. So these are the positions. Please calculate carefully. So now if you want to calculate the structure factor, you have to have 8 plus 8, 16 terms, right? If you put that one actually, so you get your the structure factor FHKL, like just like we did before. If you add, you get like this 4 times this one. So that is always positive, right? So here, this one, sodium and chloride, if they are same, they are 0. But if they are non-zero, they are different, then they are, you get the reflection from that one. That's the thing to understand. So that means just like FCC, it has to be all even, or if it is all odd, you get reflections only if they are non-equal. So that's the thing to remember. You can see, you can have all odd, like here, typically in the, if they are same, you don't get this one, right? 1, 1, 1, you never get, then 3, 1, 1, you never get, 3, 3 will you get, but if they are all odd, you always, even, you always get those numbers, right? So please remember this one. If they are all even, you get, actually they are much stronger peaks. So if they are all odd, you get, but they are much weaker ones, because these two structure, the form factors are different. So you can see 331, 511. These are very weak. So usually we call these are superlattice reflections. Superlattice means, so they have two different atoms, right? You have, say, sodium atom and chlorine is bigger, right? Sodium atom. They are different Fa and Fb. So whenever you have a structure that has different atoms, we call they are superlattice. But you have to be careful. Sometimes if you have these layers, alternating layers, we call that also superlattice. For example, this gallium arsenide, aluminum gallium arsenide, if you make this alternating layers, we call the quantum wells, right? So these are also called superlattices. Here I am talking about crystal lattice. They have two different atoms, like A and B in the lattice. We call those are superlattices. For example, here, yeah, this is what I'm going to talk about. Just look at this one. What is this? It's a real BCC, all same atom, right? So typically, if that is the structure, they are labeled as A. It's the same structure, but you have two different atoms, right? So here Fa and Fb are the same. Here Fa and Fb. Actually, this is not really BCC, right? This is what? It's really simple cubic with two atom bases, but it looks like a BCC structure. That's why we call this a B structure. So please remember, if anybody wants to follow this notation, typically if you have A1, any FCC structure that has same atoms, they are called A1 structure. But if you have a sodium chloride structure, there are two different atoms, right? They are called usually B1 structure. So if you have BCC real structure, they are called A2 structure. So then if you have like cesium chloride structure, right? They have like two different atoms, they are called B2 structures. Like that we have like A3 structure. So typically A3 is actually HCP structure. Then A4 is more like diamond structure. So here these are all same atom. Like here diamond is all carbon, HCP can be some same material HCP structure. But if you go to, anybody remember HCP, if you have different atoms, what do you call? Wood site, right? So for example, gallium arsenide, sorry, gallium nitride. So that's typically wood site. So that's a B structure, right? But unfortunately, for some reason, that is called B3. B3 is wood site. So anybody remember what is the diamond when it is different atoms? That's a zinc plane structure, right? So, like silicon carbide. So they are called typically, this is B3 structure. This is called B4 structure for zinc plane. So, but this is, if anybody wants to follow that, there are like A7, A17. For example, A7 is for black phosphorus, A17 is for blue phosphorus, and different things. But just here I just want to show A2 means BCC, but same atom, right? So B2 means it has BCC structure, but they have different atoms. So silicon simple cubic, we know that's the only atom, right? Polonium. So now if you take any of these, so you can see if you consider two different atoms, if you consider one at 0, one at half, right? If you take half, remember you get pi, that means -1. So this is, in this structure, this is non-zero, right? For this structure, what is this? 0, right? They both are the same. So please remember, for B2 that is non-zero, but A2 that is 0, because if these two are same. So you can see these superlative structures. So we know if they all are even, you get Fa plus Fb. They all odd, you get Fa minus Fb. But if they are two different atoms, this is not 0, right? You will see so that's why remember this Fa plus Fb, things like all even, right? All even one had much higher intensities like this. So all odd ones, since these are non-equal, you get some value, but those intensities are much smaller. So you can see in the diffraction pattern also, you can see, if you look at this one, what are these? These are the primary, these reflections. Look, can you see these small dots? These are basically these smaller ones coming from Fa minus Fb, because these are less intense, right? So here I can see, look at this one, 1 0 0. That means your sum is odd. That means it should be a superlattice, right? Superlattice, that's a weak peak. How about this one? 1 1. So there's your sum is 2. That means it should be a strong fundamental peak. 1 1 1. Sum is 3. That is that one that you get superlattice peaks. These are smaller ones. Can you see? So that's all coming because of that. Yes, these factors are different. Right? These are called the superlattice. If you look at this one, you see the fundamental strong peaks, and also you see the weak superlattice peaks. So these superlattice peaks are like in this spectrum, they are like the smaller peaks here. These ones are more like this strong peaks. So we showed that one right here. You remember? Yeah, here. You will see. These are the superlattices. 5 1 1 3 1. These are all odd, but you can see all even ones are strong. It's same thing in different ways. So if I put this one in some summary, simple cubic, any HKL is allowed, right? Because you get just F. If it is BCC, sum should be even. FCC, either all even or all odd. Sodium chloride, remember, only thing is all even, fine, all odd. What is the situation? If this is non-zero, you get even all odd ones, right? So diamond, so HKL all even, but if it is all even, the sum should be 4 times some factor of 4, right? But all odd is fine. So all odd is fine, but all even, not everything. It has to be multiples of 4. So HCP, don't worry about that one. Is that clear for everybody? So let's do this one. Yeah, so I don't want to, we talk about this one. So you want to leave soon?
Yeah, within 5 minutes.
Oh, yeah, let me put together this one in. So then we talk about how to calculate the D spacing. So you can show for any doesn't have to be this is a cubic structure, right? But if you take a like rhombohedral. So you can easily show this one, right? So this HKL is there, right? So, but that is pretty easy. But if you go to other complicated systems, you can see how that D is. You already did this one in the homework problem, right?
No, the
This one.
this one.
Yeah. So you can see if we go to like hexagonal or even triclinic, this is the equation for. So that's pretty complicated. We don't want to deal with these things, but nowadays you have software to do these things, right? But in this class we will only concentrate on this one. Even here we will talk about mostly cubic structure. That means ABC all are equal. Is it clear? So that's all we need to do. So before we do that one, let me quickly. Because you have to leave, right? So let's do one homework problem. Actually, it's some problem. Then yeah, maybe I'll do it in the next class.
No, that's fine. I can still like watch the video.
Oh yeah, yes, yeah. Then I will continue.
Sure. Yeah.
Okay, yeah. Okay, so we are going to look at if somebody gives you this kind of spectrum. So somebody takes some sample, we don't know what it is. You go to the XRD machine and bring me this one. So how do we call indexing. So you only know the intensity and the peak positions, right? So how do we usually figure out what kind of crystal structure is this, and also you can get the lattice parameters. So nowadays you have databases, right? With database you just compare with the database, but I'm going to show from very fundamental point of view how to analyze this kind of data. So to do this one, basically you have to just follow the simple Bragg's law, right? So if you remember, so only thing I can do this one for cubic structures. It can be diamond or even sodium chloride structure or anything, but not HCP or any other structures. So you can do, but it's too much, right? So basically what you have to know is only two things. 2d sine theta equals n lambda, right? So we'll do for the first one. So then d is given by a over k square. Remember, this is only true for cubic structure, right? Not even the orthorhombic. Orthorhombic case, only thing is you have h over a and k over b, l over c, right? But a, b, c all equal, you get this one. If you put these two together, what do you get? You get 2d is now a over square root of a squared plus l squared times sine theta, right? I just plug in d here, equals lambda. Now if I take sine squared, I square both sides to make this one get rid of the square root. Then what I get is you have lambda squared divided by 4a squared times h squared plus k squared plus l squared. So what I am going to do is, so here I have all the theta values. Actually these are remember two theta values. So then I can calculate my theta value, that means divide by 2, then take the square of that one. So that's all. So after that you just do some comparison. So let me quickly show that one. So I write down all my peaks. Peak 1 at 38.3, peak 2 at 44. And I just write down this one. Now I am going to go and calculate my, this is 2 theta, then divide by 2, calculate sine squared, right? So if you look at this one, you can see sine squared theta, suppose if you take second value, say here, if I take say sine square theta is some constant here, right? It's lambda and a, they are constant. I get h squared plus k squared plus l squared. Say this is sine 1, this has hkl. If you take sine squared theta 2, different one, that correspond to same constant times h2 squared plus k2 squared plus L2 square, right? If you divide these two, this constant cancel, what you get is, so the comparison of these two. So that's what we are going to do here. I just take sine squared, so you took theta, then take the sine theta, square that one. Now what I'm going to do is, I'm going to divide this one by that first number, because we have to divide by some reference number, right? If you do that one, I get these numbers. See whether you have any pattern. I don't see much pattern. Now I'm going to multiply this one, the next number 2. If you do that one, I get these numbers. They are also not really good pattern. Then I'm going to go ahead and multiply by 3. Now see what I'm getting. Can you see? 3, 4, 8, 11, 12, like this. So now we are going to have, this is what everybody should have. So if you have this table, everybody, I have this one. For, because what we need is this h squared plus k squared plus l squared, right? If you take primitive ones, this sum is anything, right? Except you cannot have 7. So if your body centered, this has to be, sum should be even. You can only get this. These are the numbers. If you have face centered, these numbers are this one. If you diamond, you have this one. So you need to have this one. So that's why I put it in this form. So you can see. So simple cubic, these ones. So these are the allowed ones. So if you follow this one, so which one is following this? I will do this one again next class. So what you are seeing here is, in this problem, what you are getting is 3, 4, 8, 11, 12, right? So that's actually, here you will see that one as this one, 3, 4, 8, 11, this sequence. By doing that one, you can immediately identify that is a FCC structure. So we'll do this one in the next class in more detail. So I'm going to give you a similar problem for the homework that you can, they're very simple, is yeah. Okay, so I will start from here in the next class.
Actually, we have done this in material characterization.
I think so, yeah, yes, yeah, that should be, yeah, you should be fine, yes. Yeah.
Oh, this is not.
Oh, yeah, yes, yeah. Yeah, so we'll follow this one. Before that, let me, because we talk about the atomic form factor, but we never derived that one, right? But let me quickly do that one. We'll go through this one again in the next class. So, how do you calculate that atomic form factor? If you remember how we define atomic form factor, that is basically rho r or rho. Then you have E minus I G dot r prime d cube r prime. Okay. How do you calculate this one? That's pretty straightforward. You have to usually we use for the spherical symmetric situation. If I take this one, we know how to write this d cube r prime type. So then if I pick my g vector in this direction, so then this is r prime, you can easily do this integral. How do you do that? Rho r prime e, what do you get here? G dot r prime in this theta, right? Then you get minus g r prime cosine theta. Cosine theta. Then what is d cube r prime? Spherical coordinate. You have r square dr times r sine theta d theta d phi. I don't know if you are familiar with the spherical coordinate. So this is very simple integral. Yeah, here. So this is the elemental volume here, r squared dr, then sine theta d theta, then you have d phi, right? So if you do this one, what you are getting is you have r, get r, so you get r squared dr sine theta d theta d phi. You get 2 pi coming here, right? That's it. So then you have to do this integral. So you have to integrate over r and so you can see here exactly r here r cosine theta, that is cosine theta is here, then r prime dr prime, then you have sine theta I can write as sine theta d theta, you can write as what? D cosine theta, right? Negative. So here d cosine theta is here. Then you can easily integrate that one, right? That means this one divided by EIGR here. So if you do this one, then at the end you can, that's the relationship you get for this one. Exactly. So because how do you get the sine GR? Because I have this E minus IGR, so you get minus theta to plus theta. That's why when you subtract you get E IG minus E means cos sine theta, right? Sine theta is sine theta is EI theta minus E minus I theta divided by 2 theta. So that's what we have here. Because here when you integrate from cosine theta, you get this one divided by this part. That I is here, right? That's why this GR. Then if you do from minus theta to 2 theta, so that's why you get this sine function coming here. That's it. So for the homework problem, I am giving you what is this rho alpha. You can start from here and do the integral. So I just give you hydrogen atom. We know the hydrogen atom, what is your rho alpha, then you can easily do that. Okay, I will continue from there. So that's how you calculate your atomic form factor. Actually, if you do this one, so later, yeah, I'll do this one in the next class.
Will we have another homework uploaded today?
I gave one today, yes, yeah. Because I'm not going to give any exams, it's only the homeworks.
Do we have?
I already gave next week's homework. But you guys, if you need more time, I can give you. I know these people are doing some qualifying exams, so I gave them. Yeah. Today I posted the next week's homework. I know you will have all. But for me, it's important you guys try to do it. So I don't care how well you do it. So this today's due homework. Only problem I find people find difficult is that one
Hard question, yeah.
that plane. Yeah. So the easiest thing to do is just assume you. That's otherwise it's very hard to see that plane.
We need to change the origin.
Yeah, so but it's much easier to do this way. Assume your plane as this one. What is the B? dy plus cc equals d, right? That's the equation of a plane. Then just put where they intersect, then you can find AB, C in terms of D. So if you put it here, then you get the equation. Then you know to get HKL, you just put where Y and C 0 and these two 0, then you get that. That's the easiest thing to do. Otherwise, it's very hard to see even for me. It's, you can look different ways, yeah. But you definitely have to change the origin, yes, yeah. But if you start this way, you will not have any problem.
We can come this way.
Yeah, just do that. It's very simple. Yeah. You will not make a mistake if you do this way. Yeah.